Okay, good evening, Professor David J. De Los Reyes. Okay, my topic for this session will be, this is a random topic, and I just want to, what you call this, made a lecture on long video format on one of the content gap on differential calculus. The topic for, it's now this morning, it will be applications of differential calculus. Okay, let's proceed. Excuse me. So the topic will be content gap. This is a differential calculus application. One of the application of differential calculus for those who don't know the application of differential calculus yet is in the so-called maxima minima problems. Uh, we we use what they call this differential calculus in the computation of the strength of rectangular beams. That is with the so-called study of civil engineering. Uh, why the shape of a rectangular beam for rafters of buildings are actually rectangular. Uh, the reason why it was rectangular because it was determined from differential calculus that for maximum strength the shape should be rectangular, meaning there is a depth and there is a width. Okay, let's proceed with the problem. I will try to read the problem. I write the problem so we could what you call this, visualize what this problem emanates from. The strength of a rectangular beam varies jointly as the width and the cube of the depth. Okay? Find the dimensions of the strongest beam. Strongest beam that can be cut from a log, the diameter of which is 12 inches. You assume for the meantime that this is the log. The problem is asking what will be the width and the depth of the rectangular beam that could be cut from this. We will cut a rectangular beam from this. Right? So the problem is asking what will be the depth and the width for the beam to be the strongest one. For it to be strongest, that's very what you call this necessary in the so-called erection of buildings, right? So you now know why when you go to Home Depot, something like that, the shape of beams there are actually rectangular. There are square beams, but those are different. Those are different. The application of which will be different from the rectangular beam. But for the rectangular beam, the application is different. Uh, you must have to carry some load on the depth portion for it to be, for it to be strongest. So the application of differential calculus is that we must have to determine the depth and the width. Okay, so it will carry the maximum load. Okay, let's proceed with the solution of the problem. So actually this will be the circular log, right? And from this, we should cut a rectangular beam from this. This should be the width and this should be the depth. Okay? So this half portion over here is actually d over 2. If this is the overall width, this portion here is w over 2. Okay? So from our representation, if we try to bring out the representation, okay, if you try to solve problem under applications, you must have to bring out your representation. Excuse me. the representation will be something like this. Capital letter S will be the strength of the beam, D will be the depth, W will be the width, and theta will be a variable angle. This variable angle is actually this angle here. This angle. This is the half of the width, and if we try to connect this point here and this point, okay, we will be forming a right triangle. So the angle between the half of the width and the radius, this is actually the radius of the log, excuse me. Okay, so this will be the radius of the log. This is half of the width. This is half of the depth, right? So this is angle theta. So this angle theta is actually variable, okay? So because we do not know the exact value of theta, which will give the dimension of the rectangular log to be the strongest. So actually this theta here, it could be from a certain angle, one degree maybe, or 45 degrees, we do not know. That's why for the meantime, this angle theta here is variable. Okay? And from the given figure, we could bring out a right triangle. Actually, this will be the right triangle. If this is the center of the log, and the diameter is 12 inches, of course, the radius will be 6 inches. Right? So this is the radius. This is half of the depth, and this is half of the width. Okay? We need this right triangle here to get the relation of the width, the depth, and angle theta. This depth here, width, and angle theta are all variables. These are all variables. Okay? Excuse me. These are all variables. Okay. Let's try to bring out the condition which relates the strength of the beam as a function of the width and the depth. From the given condition, the strength of the beam, okay, varies jointly as the width and the depth of the cube. So if we try to relate this given what they call this specification over here, the strength of the beam varies jointly as the width and the cube of the depth. If we try to bring out what they call this an equation from this, S will be equal to a certain constant K times the width times the cube of the depth. We call this equation number 1. How many variables we got on equation number 1? We got 3 variables. The strength of the beam is variable, the width of the beam is variable, the depth is variable, because for the meantime we do not know the value for it to be the strongest. So there are 3 variables here, right? We must have to bring out W as a function of theta, and the depth also as a j of theta. Okay, we will find this relation here. So we could place it on equation number 1. So we will be having an equation of the strength of the beam only as a function of strength of the beam as a function of theta. Okay, so our objective is actually to get the relation of the strength of the beam as a function of only one variable, because for the meantime the right hand side involves 2 variables. So we need only to bring out the strength of the beam, okay, as a function of one variable, and that will be angle theta. And to get the relation of W as a function of theta, this is now a formulation of equation, right? cosine of theta will be W over 2 over 6. The cosine of theta here will be the adjacent side over the hypotenuse. So it will be W over 2 over 6. Okay, manipulating this one, cosine of theta will be W over 2 times 1 6. We change the operation from division to multiplication. We invert the denominator. So this will be W over 2. We rewrite it. We change the operation from division to multiplication. We take the inverse of this. It should be 1 6. So W now will be 2 times 6 will be 12 times cosine of theta. So W will be the 12 cosine of theta. So we are now given W as a function of theta is this one. Okay, that will be equation number 2. We take the value of sine of theta. The sine of this angle theta here will be this side here, right, over the hypotenuse. So it will be d over 2 over 6. Sine of theta will be, again, we change the operation from division to multiplication. D over 2 times 1 6. Therefore, the unknown depth now as a function of theta will be 2 times 6 is 12 sine of theta. That will be equation number 3. So we are now given the depth of the rectangular beam as a function of theta. J theta, because they are not the same, right? So to bring out this, what they call this, the strength of the beam as a function of one variable only, we will take equation number 2 and number 3, we put it in number 1. So we will substitute 2 and 3 to equation number 1. So S now will be K times W, but what is W? W is 12 cosine of theta. This is 12 cosine of theta. And what is the depth? 12 sine of theta, but this should be to the third power. This is to the third power. And if we try to, what you call this, expand this one, there will be a 12 square over here times 12. That will be 20,736 times K, okay, times cosine of theta times sine cube of theta. And to simplify calculation, for the meantime, we do not need this K here for the meantime. Okay, so we will let, C to be equal to 20,736 K. Okay, so the strength of the beam now will be capital letter C, which is this, times cosine of theta, sine cube of theta. Okay? So after deriving S as a function of theta, okay, we will take the first derivative. ds over d theta will be, this should be C times this trigonometric function here. So it will be C times the derivative of cosine of theta, sine cube of theta. First function, second function, the operation is multiplication, right? So C, open bracket, first function, the derivative of sine cube of theta will be power formula, 3 sine square of theta times the derivative of sine of theta, it will be cosine of theta, plus the second function, sine cube of theta, times the derivative of cosine, it will be negative sine of theta, close bracket, okay? And under maxima minima, for maximum strength, okay? That's why this is now an application of differential calculus. Without knowing differential calculus, we do not know how strong that beam will be. So by using differential calculus, one of the content gaps, okay? We will set ds over differential theta equal to 0 for maximum S. Maximum S meaning strongest. Okay, so without knowing differential calculus, we could not find for the strongest beam. So one of the applications of differential calculus is actually in the computation of the strongest beam possible in our practical applications or lumbers. Okay, So we will set ds over differential theta equal to 0 for maximum. Because if we try to graph, right, there will be an S. This is, what they call this? This is S, and this is theta. And at this portion here, we could say that this is a maximum point. And we are looking for this one. Okay? Maximum value of S, okay? Which will satisfy, which will compute for the unknown depth and width, right? We are after the maximum. Because if we try to take the graph of this, it should be something like this. That's why the subject matter is maxima minima. Okay? So without knowing differential calculus, we do not know if the depth or width of our beam should be the strongest. So for it to be the strongest, we will let ds over differential theta equal to 0 for maximum S. Okay? So if we try to put this to 0, we set it to 0, right? And again, we divide both sides by C. This C here cancels, right? So it seems there is no more C over there. And 0 over C will still be 0, right? Right? So what comes out will be this equation here. It will be 3 sine square of theta, cosine and cosine will be cosine square of theta. A plus and a minus will be minus. This is sine to the third, sine to the first, so it will be sine square of theta times sine square of theta, or actually, this two here is actually sine to the fourth of theta. I just placed this one as sine square of theta so that I could divide immediately the left-hand side by sine square of theta. Okay? So this sine square of theta cancel with this. What remains will just be simply 3 cosine square of theta. The second one, divided by sine square of theta, this sine square of theta cancel with this. Okay, so this will be minus sine square of theta actually. And this should be equal to 0. Actually, I expedited a little bit. Okay, I put the equal sign here. So I transpose this negative sine square of theta to the right hand side. It is something like that, right? Okay. Then we will try to divide both sides of the equation by cosine square of theta. We divide this by cosine square of theta. We divided this by cosine square of theta. Okay. This cancels. Okay. Second power, so it will be sine of theta over cosine of theta, all quantity square, equal to 3. Then we try to, but sine of theta over cosine, that will be trigonometry, that's tangent of theta. This is tangent square of theta actually. This is 3. So to compute for the value of tangent of theta, we raise both sides of the equation to the 1/2. So these two here cancel with this. So tangent of theta will be 3 to the 1/2 will be the square root of 3. So actually tangent of theta is actually square root of 3. So from this we could bring out a right triangle in which the value of tangent of theta will be opposite over adjacent. Now this is square root of 3, this is 1. So the hypotenuse will be the square of this plus the square of this, then take the square root, it will be 2. And in here, we can compute for the value of sine of theta. Sine of theta will be opposite over hypotenuse, square root of 3 over 2. And cosine will be adjacent over hypotenuse, it will be 1/2. So we now know the value of sine of theta and the value of cosine of theta. So if we try to go back to equation number 2, we could compute for the width, unknown width of the strongest beam. Okay? It will be 12 times cosine of theta. 12 times 1/2, or the width now will be 6 inches. And for the depth, we will go back to equation number 3. It will be 12 sine of theta, right? So this is 12. Sine of theta is actually square root of 3 over 2. This is square root of 3 over 2. 12 over 2 will be 6. So the unknown depth now will be 6 the square root of 3. And if we try to use our calculator, 6 times 1.732, it will be 10.39 inches. So for the beam to be strongest, okay, the depth should be 10.39 inches and the width should be 6 inches for the beam to be strongest. Okay, that is an application of differential calculus. It's very, what you call this, important because without knowing differential calculus, we do not know the depth and the width for the beam to be strongest. So that's one application of differential calculus. I will check my camera. Okay, that's it, guys. So for those of you who are taking or looking or browsing a content gap on the application of differential calculus, this is one of the examples. It is on the so-called maximization of the strength of a beam needed for our rafters in our buildings. Okay, so we now know why the shape of our rafters used in our buildings are actually rectangular. Okay, that's the reason why it is rectangular. The depth should be 10.39 and the width should be 6 inches. Okay? Okay, that's it, guys. So for those of you who are looking for the content gap on the so-called differential calculus, this is one of the examples. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes.